Hello, welcome back to today's AutoML lecture. Today we will talk about one-shot techniques in NAS. So the motivation for this lecture today is that black box search strategies, for example, Bayesian optimization or evolutionary algorithms, train each architecture independently from scratch, which is a very expensive approach. However, the key insight is that architectures in the same search space also share common operational layers. So therefore, the question is, can we exploit the structural overlap to avoid redundant, unnecessary, expensive training? With the key question of, is it possible to train all architectures at once by sharing weights across them and select the best one without any additional training? And that's where the very efficient NAS method one-shot methods come in. So we have seen this figure already several times, having the search space defined, and now we want to have one one-shot method, which jointly learns the architecture with their weights. And the idea is that we have a one-shot method, a so-called super network, which is a large model that has all architectures in the search space as submodels or also subnetworks, which allows for weight sharing across architectures. And the idea is that we only need to train this one-shot model once, and then therefore implicitly also train an exponential amount of individual architectures with it. And after training the super network once, we can inherit the weights from the super network for individual architectures for evaluation. So let's dig deep. So the overall idea is based on directed acyclic multigraphs to capture all exponential many cells in cell architectures. Why cells? So the idea of one-shot methods became very popular in cell-based search spaces, so we will focus here also mostly on cells now. So as I mentioned, we have a directed acyclic multigraph where the nodes represent tensors or feature maps and the edges represent the computation between the nodes. So having a multigraph means we have several operation edges connecting the nodes with each other, and therefore the combination, which could be an addition or concatenation of the operations, result in the actual operation on being the node here. So the overall idea is that the individual architectures are subgraphs of this multigraph. So we can see here our overall super network with several edges connecting these two nodes with each other. And our subnetwork is one directed acyclic graph, meaning we have no multigraph anymore, therefore having only one edge connecting these two operations with each other. And the very important in a one-shot method is that the idea is that we train an architecture that shares layers with another architecture, and you share the weights and train all at once. Meaning that the weights for the operation, for example, here for that operation on that particular position, is shared for all the architectures and all the different subnetworks having that same operation on that same position in the overall super network. The overall architecture optimization problem is here that we want to find the optimal path from the input to the output. So very important here again, the weights for the operation on that particular edge are shared over all the architectures having that operation on that position in all of the subnetworks. So how can we actually train that one-shot method? Since we have an acyclic graph, we can easily do some backpropagation with an optimizer, which we are mostly interested in using, for example, Adam, to train the whole subnetwork, train the whole super network at once. This implicitly therefore trains also an exponential number of architectures, as already mentioned. However, one potential issue by doing that is a co-adaptation of weights. So we implicitly optimize the weights to work well on average across architectures, but they are not optimized specifically for the top performing architecture, and also not that one network performs better than the other or one operation performs better than the other. So it mostly has to work well on average. And one option to mitigate that is to use drop path, which is kind of a very analogous way to drop out. So what it's doing, at each mini-batch operation, we have kind of our one-shot model. We zero out one edge with a probability P for each operation edge. So for example, here at our batch 1, we have only our yellow edge connecting these two nodes with each other. At batch 2, we don't have the yellow one anymore, we have a green and the blue one. So therefore, the overall idea is kind of to overcome the interdependencies between both of these operations at each position, and therefore focusing on this operation being able to learn by itself without being codependent on these two other operations as well. Another idea is to schedule this probability by scheduled graph path. So we start with a probability being 0 and then increase the probability linear to a predefined maximum probability over training. So the idea here is that we want to, at the very beginning, we want to get all the weights to get kind of decent average performance, and over time actually increase the probability to relatively large values. And in the limit, one could say that the maximum probability becomes to a very large number or even 1, meaning you would drop out all the edges, which doesn't make really sense. So therefore the trick the authors propose is to drop all the edges but 1, and therefore do exactly what one would do at sampling, which we will talk about next. So therefore resulting in a subnetwork, one particular subnetwork, and just training that at a time, and train therefore the weights for that particular subnetwork at a time. So we mentioned sampling, and now we want to look more into sampling. So sampling means that at each mini-batch operation, instead of training several edges and computations, connecting two nodes with each other, we sample one single architecture from the search space, and therefore update the parameters of that one-shot model corresponding only to that particular architecture. So here we can see again kind of a visualization. We have our one-shot model here, and for the mini-batch iteration 1, we only have one edge, one subnet having the connections, connecting the nodes only by one edge. Here we see we have a different subnetwork which is trained for batch 2. And there are several different approaches one could do in the literature. For example, using sampling the architecture, sub-architecture from a uniform distribution. That is what we do in random search with weight sharing, uniform sampling. So we sample one sub-architecture from a uniform distribution, which is a very simple and surprisingly competitive approach in combination with a random search eventually happening. Another approach which actually came historically earlier is ENAS, where the idea is to learn a neural network controller to learn a possibility for when to sample which architecture. And another approach is the single path one-shot method, which also samples uniformly a path and then does some evolutionary search over the trained super network. Also here we fully decouple the super network training with the architecture search. So now we trained our super network, being it all together or by sampling approaches. Now the question is, how can we actually utilize the training of one-shot models? So how can we select the best individual architecture? And there are several strategies. So the most simple one is just like sample a certain amount of architectures, let it be here capital M architectures uniformly at random, and rank them by the validation area using the super network weights. So how would one do that? We would sample our architectures, our M architectures, and we would inherit the weights. So just like initialize those networks with the weights from the super network, do a forward pass on the validation data, and therefore evaluate for the validation performance. And then you could just like rank all of these architectures. One could also additionally optionally return the top architectures and retrain them from scratch for full training. So you would look at the best architectures based on the ranking from the super network and retrain the best one from scratch for full training, and then do some evolutionary or Bayesian search approaches as well, using, for example, the supernet weights instead of just like sampling from scratch. Using the super network weights, so the one-shot weights more or less as a guidance, so performance estimation strategy. That's what also can do. So random sampling, uniform sampling, or using the super network weights as a performance estimation proxy in combination with an evolutionary or Bayesian optimization search. However, the overall pitfall is, and the kind of idea why we could use it, is that the correlation between the architectures evaluated using the one-shot weights and the weights retraining the network from scratch should be high. So our goal is to have a high correlation between our one-shot model accuracy and our standalone model accuracy. However, that is not always the case, and it's currently also a persistent challenge in current research because the ranking correlation is often low in practice, which we call the ranking disorder. Reasons can be any kind of weight co-adaptation and insufficient SuperNet training, so maybe that the super network in the training process is focusing on certain operations instead of on the others, and eventually also maybe a mismatch between the super network and the sub-architecture batch normalization statistics. But also here we have several mitigation strategies in the literature. For example, greediness introduces multipath sampling with a redirection filter for the weak paths, and greedily trains potentially good paths, so focusing on the good architectures and the good paths within the super network already during the SuperNet training. We could use a prior guided one-shot NAS approach using zero-cost proxies as an auxiliary ranking loss. Another approach, shift NAS, learns a sampling distribution to adapt to the subnetwork complexity during training, and the complexity-aware learning rate scheduler is also looking at the complexity of the subnetwork and therefore adjusts the learning rate based on that complexity. So now we talked about one-shot models being trained once, and you can inherit the weights for the subnetwork from the SuperNet. One particular important part is here also the scalability and the efficiency. So a linear increase in the number of candidates causes a linear increase in computational costs for training an exponential number of subnetworks. So you can train an exponential number of architectures and linear compute costs using a super network. However, with the key assumption that the ranking of the architectures under the super network is relatively consistent to the ranking of the independent training. However, important to note is here that the super network allows for a quick evaluation, so we can have a kind of a good proxy of the performance of the particular architecture, but we still need a search strategy. It could be random search or also evolutionary or Bayesian optimization. And in total, the most important insights from this video, which we talked about today, is that all possible architectures are subgraphs of the single large supergraph, which share weights across architectures. We could use drop path and schedule drop path to prevent any kind of co-adaptation by randomly zeroing out operation edges. One of the biggest issues in one-shot methods is a ranking disorder, or that the ranking correlation between the SuperNet and the sub-standalone models is not the same, which still is a kind of a key challenge. And then we talked briefly about some mitigation strategies to overcome that challenge. And thank you very much for listening. See you in the next video.